Hi, good day to all once again. And this is Rayan, and the topic that I'm going to discuss is the effect of micromechanical properties on the buckling behavior of a woven composite plate. So we will adapt ANSYS material designer once again to solve this problem, and we will see the mechanical properties like the yarn spacing or the fabric thickness, how these parameters are affecting the buckling load of a composite plate. So this is me, Syed bin Rahan, and along with me, MD Mazedur Rahman, and both of us has contributed same for the research outputs. And we are from Northwestern Polytechnical University, which is located in Xi'an, China. So let us look at the research contents. So we will at first talk about the micromechanical properties of woven composite material. What will be the parameters? Then we will see the analysis procedure, and then we will see the buckling condition, which buckling condition we will use actually to solve this problem. Then we look at the material definition, the material properties that we have used for this research, and finally we will discuss about the parametric results. So let us look at the micromechanical properties at first. So the RV shapes and ply type, of course. So at first, let us look at the plain woven composite RVE and ply. The left one is the RV design, and right one is the macroscopic ply that we can see actually in practical engineering. And here we have the 2 woven composite RVE and the ply type, of course. So we can see there are differences, especially the difference comes from the weaving type, whether it is a plain weave or a twill weave. So what are the properties, other properties that we are going to check? So we will see how the effect of fiber volume fraction on the buckling load. Then we will see the yarn volume fraction. Then we will see the fabric thickness, and finally we will see the yarn spacing. So these are the 4 different mechanical properties that we are going to study. So this is the summary, we can say. So changing the value of all those micromechanical properties will be studied for a woven composite plate under compressive loading condition. So this is the analysis procedure, as we can see. So at microscopic scale, as we have described earlier, homogenization will take place. So in meso scale, after homogenization, we will find the elastic constants for a single ply, and then after that we will use that ply for a combination of plates, and we will find the critical buckling value for a macroscopic scale. So these are the buckling conditions, these are the boundary conditions. So we have assumed the plate thickness as 2.4 mm when each ply will be 0.15 mm thin. The plate code will be used as 0 degree, 45 degree, minus 45 degree, and 90 degree 2s. I mean this is a symmetric condition and quasi-isotropic plate, of course. And as for the boundary condition goes, one end is fixed, as we can see. The loading edge is simply supported, and other 2 edges are free. And along with the boundary conditions, we can also find the length of the plate, which is 300 millimeter, and width of the plate is 200 millimeters. So the aspect ratio of the plate is 1.5. So these are the material properties that we are going to use. For fiber, we will use the carbon fiber, and these values are available in ANSYS material library. So we have taken the fiber values from the material library, And for matrix, we have taken the value from the literature. So let us go to the results. The first result is the effect of fiber volume fraction. So as we can see, as the fiber volume fraction increases for both plane and two wheel case, the buckling load increases significantly, we can say, and in some cases up to 35%. So another interesting thing is that while the fiber volume fraction is increasing, the difference of buckling loads between plane and two-wheel wave is also increasing significantly. And right side we can see the fabric thickness, yarn volume fraction, shear angle, and yarn spacing. These are the values. We take those standard values and kept them constant, and we just increase the fiber volume fraction to see the effect of fiber volume fraction on the buckling load. We will see the effect of yarn volume fraction. It is quite interesting actually. Unlike the fiber volume fraction, increasing the yarn volume fraction will decrease the buckling load. It's like approximately 1% of increasing the fiber volume fraction will decrease the buckling load by 1% approximate. And right side again we can see the fabric thickness and fiber volume fraction and EN spacing data. These data were kept constant while we increase the EN volume fraction. So let us look at the results for the fabric thickness. As we increase the fabric thickness, the buckling load decreases slightly. But if we look at the scale factor, these reductions are not significant actually. In general, we can conclude that for both plain and two-wheel cases, increasing the fabric thickness has a very minor effect or no effect actually in terms of stability of the plates. Next, the results for yarn spacing. This is quite interesting because before the analysis we thought increasing the yarn spacing will decrease the buckling load, but actually increasing the yarn spacing is significantly improving the buckling stability of the plates. For both two wheel and plain cases, we can see the significance of increasing the yarn spacing. But one important thing to notice here that the buckling load increases sharply when we are increasing the yarn spacing from 0.5 to 1.25 mm, and after that I mean after 1.25 millimeter, this even though we are increasing the yarn spacing, the amount of buckling load is not increasing that much, so the effect diminishes, we can say, after the yarn spacing of 1.25. Finally, let us look at the conclusions, the key findings of this research. So increment of fiber volume fraction increases the buckling load significantly, and in some cases up to 35%. Then increment of yarn volume fraction, as we can see, it will reduce the buckling load, and roughly 1% of increment of yarn volume fraction would lead to a 1% reduction of buckling load, and this is an approximate. Sometimes it's 0.9 to 1.1%. So increment of fabric thickness, no significant change in buckling load of plates, and increment of yarn spacing, of course, it will lead to a significant amount of buckling stability up to 1.25 mm, and then the effect diminishes. So another important conclusion is that for any given condition, the 12 woven are better in terms of the stability of plates than plain woven composites. So thank you very much for listening me. If you have any research question, you can find me. This is my email address, and you can reach me. I will be really glad to answer any question regarding this research. So I wish everybody a happy life, and thank you very much for listening my presentation.